In part C of this pulley question, we are taking a look at pulley A, only pulley A, which is the same pulley A that we had in part A. The difference being that instead of a force being applied through a spring scale, we have a mass hanging here. But that is also applying a constant force. So it functionally is exactly the same as part A. So we're shown that it's attached to part A, pulley A, excuse me. It's released from rest, so that means omega naught equals 0. How does the net torque and the magnitude of angular momentum are changing, if at all, during the time it's released? So let's tackle net torque. First thing we'll do is put down the formulas we know for net torque. And so we've got the net torque is I alpha. And the other formula we have for net torque is RF sine theta. Now it turns out we can use either or both of these to explain it, and I'll do both for you. In this case here we have I, which we know is unique to the object and is proportional to IR squared. Well, and the I, excuse me, is mr squared. It's proportional to mr squared. The mass of the pulley isn't going to change, nor is r, so this will be constant. And the acceleration, well, the acceleration, the angular acceleration, is caused by the acceleration of block M. And block M is accelerating because of gravity. And gravity is not changing. So we would say that the net torque would be not changing, and that is because the momentum of the moment of inertia, the rotational inertia, is not changing, nor is the alpha, which is caused by gravity accelerating it. So that's the first piece on the net torque if we went about it with this formula. If we use the second formula, well, we have R, which is constant. The F in this case is the weight, Fg, of the object that is accelerating it. And sine theta, that is the angle, and this is the point of contact where the force is being applied, is not changing. The angle is not changing. The geometric relations between the force and the pulley are not changing, nor is the weight. So that's why it's not changing. Two lines of evidence, and we can easily rock it, but we could choose either one of those to answer. The next question is a little more difficult. It's a little more difficult. The angular momentum, and just like P equals mv for linear momentum, rotational momentum, L, is equal to I omega, where, of course, the moment of inertia is like the mass inertia, and the rotational velocity is like the linear velocity. And we can just use that right there. Or we could use V omega R. No, we're not going to use that. We're just going to use L equals I omega. That's just easier and simple and straightforward. We've already argued that I remains the same. And so above, so we already got a solid argument for what happens with I. Omega itself is the rotational velocity. And the rotational velocity of this thing does increase. We know that V equals omega R, and the distance, the linear distance that this block drops will be equal to the arc length, that part of the circle that is traveling as well. So the two are directly proportional to each other through V equals omega R. R remains the same. Velocity increases, so therefore so will omega in that particular case. So we know the omega is increasing. So the angular momentum will increase, and we will explain it in words the similar way we explained the first part. That's part C.